let's shine some light on our future. There it is, off in the fast one. Okay, so let's see where we are here. It's week 6, believe it or not, and so week 6, I'm going to launch exam 3 on Thursday, and also by now, I think everyone's taken, almost everyone's taken both exams, and I've received the majority of summary ones. For whatever reason, I don't know, I checked last night, I only saw one summary too. So let me dip into the website and just remind everybody, there are 2 submission links for each summary. I think this might be what's going on. So there's summary 1. Here's where you upload your summary for me to grade. And you can see there are 25 people in the course. 13 have submitted. I've finished grading, this morning at 7 a.m., so looks like 3 people submitted summary 1 this morning. So that's where it has to be submitted.
I thought we were on summary 2.
We are on summary 2.
We are,
At least
okay.
I am. There are a few people who are still on summary 1.
Oh,
But, so I'm going to make that a little larger. In order to be graded, summary 1 has to be uploaded to this upload site. You also do need to put it on the, hey Matt, you also do need to put it on the forum for peer review, but that's where it has to be in order to be graded.
I don't know if it's just different on student Moodle pages, but
Yeah.
the summary button isn't like up there in red usually. It's like down below.
I think it should look just like this, won't it?
I don't know, mine doesn't look like that. Like it would say upload someone here, right? And
Yeah.
then you click on that, and then there's usually like a.
You'll see a different view. I mean, there might be a way I could go into
Yeah,
student
so
view or
it's really fine. I just want to
something.
make sure it's like hitting it the right thing.
Yeah,
It's all good.
right. I think,
You got the name right today, too. Thank you.
you're welcome, my man.
Thank you.
Told you I'd get it
Yeah, you got it.
eventually. This is what the student view looks like, so I can click on, so here's what it looks like in your,
Yeah.
yeah. So,
Perfect. Yeah.
click,
Summary 1 is your article, correct?
that's right, yeah.
Okay.
Oh, so yeah, because I just always see the ad.
Add submission,
Yeah.
And then that's where you upload it, yeah.
file submission. And you can either just drag it right in here from your desktop, or you can click on that button.
You can literally just drag it and
There's
drop
2
it.
ways to do
Yeah,
it,
that's awesome.
Yeah.
yeah.
But you can only do, I'm taking GIS as well, and Moodle only allows you to upload 1 file. So you can't upload like 2 files.
Well, do you need to upload 2 files in this course? Is that what you're saying? Oh, yeah.
No, I'm just saying that you're only restricted to 1 file.
Not necessarily. The instructor has control over that.
Oh, okay.
You could have 10 files in there if I let you,
Oh,
but
okay.
you don't need to upload 10.
Because I was running into that problem in my GIS.
Yeah. Well, let me know if you run into it here, and I'll
Oh, yeah,
fix it for you.
no.
For sure. Okay, so there's summary 1. Summary 2.
Did it on the forum, and did we find some other things that we did at the solution? Sorry,
Yeah, no problem. So, summary 2, I'll just dive into the forum here for a little bit. Which money pit is better? Any more there, Steve? Not a problem. So I'm not gonna dive into these now, but one thing I also would like, just go ahead and add your
Yeah, I was just thinking.
photo. It doesn't even have to be a headshot, it could be your pet or something, but
I'm
just,
doing a mermaid pose.
mermaid
That I
pose
saw
works,
2
that works.
months ago.
same thing here. So this is good to see, 2 replies per post. Mermaid, is it underwater mermaid or?
No, just Matt Seaton. You'll just see me. I mean, you can't miss it. There's summary 1 with that, because I already submitted yours, and my picture will be in there.
Super. Okay. All right. Well, I think we're cruising along here pretty nicely then. So we finished up Cole. Summary 2 was more or less the forum for last week. And, now I'm I'm excited for this lecture. I'm going to see just what's in here. All of these board notes that you're seeing now were from prior semesters. I found a lot of times I'd post these things, and so this was posted spring of 2015, and it's roughly, so you'll see right away, okay, that was 2015. You'll see roughly we're on the same schedule. This was when Mark Olson was teaching, so he's got the same kind of notes, we've got,
DET.
yeah, energy's power times time, here's his heat engine. Specific heat capacity, we did talk about that a little bit. So Q is the symbol for heat, thermal energy. Mass is how much there is. This is the specific heat. I think we had an issue with that on the last quiz, just the answer. And Tim has graded those. And here's the change in temperature. So that's just the thermal problem. So he's gone through that. He's gone through a steam problem. Perfect. Okay, and we're going to get into this Carnot today. This is also a great topic to hop onto. Thermo, and he's got the 3 laws of thermodynamics. Fantastic. All right, so all of that is good and valid from a couple years ago. Yeah, no, Mark did a nice job with this. Summary one review. And so we're just recapturing these. This looks like my notes, but I forgot to rotate them. This is just a Carnot efficiency example. We will go through that too. Okay, and here you start to work the problems. All right, so let's just go ahead and get into chapter 6. Like I said, these even chapters tend to be my favorite. They're sort of more physics based. Kind of the meat and potatoes of energy technology, if you will. So chapter 6. This is heat to motive power. Now, what's just kind of strange about that right off the bat? Because we've already talked about all the types of energy, heat being one of them. When we started chapter 4, we talked about motive power, basically kinetic energy, things flying around. We also did the example where the kinetic energy of wind created electricity and heat. So what's kind of strange about this? Heat to motive power. And it's kind of backwards in ways, right? I mean,
in itself, it can't really generate power.
Well, I mean, we'll see shortly that heat does generate power, but it's sort of like fighting an uphill battle, if you will, if that makes any sense. I'll show what I mean by that. But let's take a look, because heat is typically the lowest form of energy, the least useful in a lot of ways. It's sort of a waste product of a lot of other things that we typically use. Is
It's the oldest, to our knowledge. Old caveman's got a hold of it.
Well, right. You can think of the caveman keeping warm around the fire. But here we go. Here's how the ancients did it. I think this is called Hero's steam engine. And really all you just have a fire here sitting beneath some type of vessel. There's going to be water inside this vessel, a couple little spouts, if you will, not valves, but just piping, just tubing. There's a bearing here and a bearing here that allows the sphere to rotate. And so obviously here's your heat, Where's the heat energy coming from in this case?
Wood or coal or.
Yeah, what type of energy is wood or coal?
Biomass,
What type of energy is biomass? It's the same as wood or coal.
so carbon,
Keep going. It's the same, what type of energy is carbon plus oxygen?
combustion.
Keep trying.
God, we're
Take-
digging deep, okay.
Take a look on the periodic table over there.
I don't know if that's from here.
It's chemical energy. It's just chemical energy, yeah. So,
Okay.
yeah. So you've got the chemistry there. The carbon is sitting here. The oxygen is sitting here. So the chemical energy becomes thermal, becomes motive or rotational. Now, this thing isn't going anywhere. They don't have a steam turbine hooked up to it to, make electricity. It's not on a car, so you're not driving anywhere. It's just sort of a parlor game or curiosity, if you will. Same thing here, heat, water inside, steam comes out and spins this flywheel. So you can imagine, I'm going to hook this up and make, grind some flour or, maybe pump some water, just, move something around. So we're going from heat to motive. That's the point. All right, now, this is also pretty cool, pretty involved device. And I'm just gonna, since it's so well drawn, I've tried to draw this thing in the past, but it doesn't go that great. So I'm gonna walk you through this little contraption. And kind of the interesting thing about this technology is that it actually enables the extraction of more hydrocarbons. Because what's down here, it's water, whereas it's sitting in the well, and that's not what you want down your well. You want to be able to either go down there to mine coal, or you want to go down there and pump oil out of the ground. So the water underground is sort of a liability. So let's see how this thing works. You've got the boiler, and what the boiler is doing, when it gets hot, it's in with valve A open. So you can think of this as a cycle. Just like in your combustion car engine, you got a cycle, you look at your tachometer, it's running 3,000 RPMs. This thing might run 1 or 2 RPMs, because there's actually someone standing here putting wood into the boiler with their hand on this valve, allowing hot air to come in. So as this comes in, it gets higher and higher pressure, this valve C is closed because the pressure inside here closes it. Now, as soon as I allow this pressure to build, I then open, I don't know if it's shown on here.
D right there.
Yeah, eventually, it's not really shown like what the pressure value has to be, but once I close this, the pressure is high in here, and it just sends the water out the stack. And then you close it again, build this up. The whole time, you're also allowing this cooler water to come down into this pan and thus cool it. When that cools, it creates a vacuum and sucks more water up into it.
Oh.
So the water is actually being sort of sucked back up into this guy. So it's being overpressured to work in that direction, underpressured to pull up the next batch of water. Yeah.
So, like, what year are we talking about?
We're talking late to mid 1800s.
Okay.
Yeah.
Okay.
Yeah. Late to mid 1800s. This is, I'm sorry, 1700s. Yeah,
Okay.
England. This might have made its way to the Americas in the 1800s, but Savory's 1698 steam engine and it's called the Miner's Friend.
Okay.
Yeah.
Wow.
So when the pressure is high, it sends water up, and when the pressure is low, it sucks water back into the vessel?
When the pressure's high, it sends water up through D. It actually sends steam out through D. When the pressure is low, after being cooled, D closes, C opens, and it pulls up. That's kind of what we're,
Evaporating the water more than just pumping it to a different location?
it's not evaporation happens at ambient temperature. It's boiling.
So it's turning into steam?
It's turning it into steam.
And then just escaping into the atmosphere, whatever?
Yep.
Pumping it up?
Yep.
This is
Seems
remind,
like such a waste of water, like just so you can go mine or whatever.
Well, what's your alternative? I mean, it's, otherwise you've got, you're waiting for the wind to blow. You wait, because you don't just go plug something into the wall. You don't just plug your, into the wall in 1698.
I guess basically what I'm saying is like to just like have all that water evaporate, like, and then we're just kind of in a water crisis now. It's almost like, it just doesn't seem like the most efficient way to like,
Well,
to do it.
I-
Like if they want to remove it and move it somewhere, I understand that. And like, we have water tanks, we had fire trucks back then, you know? So like we could have easily transported that water somewhere rather than just letting it all evaporate, you know what I mean?
Oh, well,
once it
no,
evaporates, it goes back into the
I think
cycle.
it's still in the cycle, yeah.
Kind of, but not as an aquifer, now it's dispersed, you know what I mean?
Well, then it rains
Rain,
down
You
and
can't
then,
drink rainwater, it goes into the earth, and then.
Well, sure, I mean, the aquifer is there and fine, but it's in the way of your fossil fuels,
This is probably the least of mining's problems,
yeah.
maybe wasting a little water.
Yeah,
I
it's a good point.
didn't realize they did that, I didn't realize they removed water aquifers to get to fossil.
Oh, yeah,
fuels,
yeah. Oh, yeah.
nowadays, we don't do that. That's not how it's done nowadays at all. Because I was a patrolman geologist out in North Dakota for the last 6 years.
Yeah.
And nothing like this. We just,
Well, you're much deeper than this, you're well below the
yeah,
water
yeah.
table.
Plus, we go way past the water table and we cement and, I mean, there's like 6 to 8 feet of wall, impermeable surfaces between the water table and the
Yeah,
hole.
yeah. So this is low power,
This reminds
pretty
me of
high
the
tech for
Romans.
1698, but pretty low tech, yeah.
This reminds me like the Romans and their old bathhouses that they used to have they heated.
Yep, yeah,
Maybe not like this, but I mean with like the heat and pressure
sure,
and
yeah, absolutely.
the boiler system.
Yeah, okay, so the next step, we move on from Savory to Watt, and I think there's a picture of James Watt sitting right there, kind of looking Washingtonian, figuring it out.
All washed up.
All washed up. But he devised a different way. So again, you still have your heat source. This is your cold source. So as if this is closed and you've got water build up, it sends this piston up. And then again, when this cold water comes in, sucks it down, thus pulling this guy up. So you could run your, you could even pump water out of the ground here, or pump petroleum. The advancement here now is the water is now more or less enclosed, and there's a condenser. So in this case, the condenser is allowing the heat exchange to happen faster. Rather than just so again, we talked about that before, the difference between heat and temperature. Two things can be the same temperature, but one will feel colder because of the heat transfer. Same thing here if you have ambient air cooling that down. Now the piston, rather than just being sort of pushed up or sucked down, you can see that there are valves on the top and the bottom. So as one is pushing, the other is pulling. So almost like a four-stroke engine. Almost like a four-stroke engine. Now, out here, you also have this flywheel. The flywheel is more or less smoothing out or dampening out any little irregularities in the system. Because it's the power stroke is varying. It's sinusoidal. So the flywheel allows it to sort of be smoothed out, if you will. And then you could, drive all kinds of stuff. You imagine you're driving a lathe or a drill, or I don't know if the cotton gin has come online quite yet, but any one of these stationary mechanical things, or a loom. Question?
You answered my question. I was going to ask if the purpose of this apparatus would serve the same as the previous.
Absolutely, yeah. It just allows for a greater diversity. And if you look back some of the old industrial age photos. You'll see the drive shaft sort of running above the shop floor. People are just kind of, strapping into those.
There's at the old fort, there's that old sawmill, the Historical Sawmill Association there.
Yeah?
Has that old locomotive,
Steam driven?
steam
Nice.
driven,
Steam locomotive.
sawmill.
Mm-hmm.
And so it's got all these big belts, and I mean, it's ancient.
It's cool. It's cool.
But that reminds me kind of like.
Yeah,
the
it's very
old
similar.
technology.
Yeah, steam powered. Okay, so there's James Watt. This has to be one of my favorite photos. So here's Trevthick, and there's a neat little, okay, here we go. Richard Trevthick, a Cornishman and a brilliant and adventurous engineer, was looking at many options and attracting threats of lawsuits from Bolton and Watt. Nevertheless, he continued his developments, and on Christmas Eve, 1801, this is like right out of Chitty Chitty Bang Bang, Christmas Eve, 1801, a startling result emerged into the twilight. The age of steam locomotion had begun. So he took, Watt, who was sort of, just sitting here stuck on the ground, put the entire system on a buggy, horseless carriage, there it is, cranking away, right down the streets of London or wherever he happened to be. Okay, so those are the two, and then another, just while we're on that topic, so let's just do a little bit of units conversion. So 1 horsepower equals 746 watts. So you can see almost immediately where those two things are born. So there's your horseless carriage. So how many horsepower? How fast can you go? That's always the question. We've gone to these
That's where it
Shellyco,
comes from.
absolutely. We've gone to these Shellyco Marathon races, and everyone wants to know, how fast does your car go? Well, the point is not to go fast. The point is to go far with low energy consumptions, to be efficient. So, but again, you imagine, okay, 1 horse, 2 horse, up to 8 horses, and maybe this one, and I think it's in the book here. It'll tell you exactly how many horsepower this is. But there's your horsepower, and there's your brain power. James Watt. Takes 746 watts to make 1 horse. Okay. Let's just I'm going to take one little recording break, and then we'll get back in. There's some neat math in this chapter I want to show you.